So next we'll prove a corollary of the previous theorem. If A is an invertible matrix, then the products A times A transpose and A transpose times A are also invertible. So proof. Let the matrix A be invertible. Then, by the previous theorem, the transpose of A is also invertible. And since the product of invertible matrices is invertible, the products A times A transpose and A transpose times A are invertible. So as a second corollary of the previous theorem, if the matrix A is invertible and symmetric, then the inverse of A is symmetric, so proof. Let A be invertible and symmetric, then the inverse of A exists and A is equal to its transpose. And so the transpose of A inverse, which is the inverse of A transpose, where A is equal to its transpose, is equal to A inverse, and hence the inverse of A is symmetric. So the theorem let A and B be square matrices of order n with real entries, and let K be any real scalar if the matrices A and B are symmetric, then A transpose is symmetric, the sum A plus B is symmetric, and the scalar multiple K times A is symmetric. So proof. First statement. As the matrix A is symmetric, A is equal to its transpose, and so the transpose of the transpose of A, which is the matrix A, is the same as the transpose of A, and hence A transpose is symmetric. Second statement, as A and B are symmetric, we have that A is equal to its transpose, and B is equal to its transpose. And so the transpose of the sum, A plus B, which is the sum of the transposes, where A transpose is the same as A, and B transpose is the same as B, and hence the sum, A plus B, is symmetric. So third statement. Again, as the matrix A is symmetric, A is equal to its transpose. And so the transpose of the scalar multiple, K times A, is the scalar K times the transpose of A, where A transpose is equal to A, and hence this is the scalar K times A, and hence the scalar multiple K times A is symmetric. So new theorem, let A and B be symmetric matrices such that the product A times B is defined then the product A times B is symmetric if and only if the product of A and B commutes So proof, let A and B be symmetric, and suppose that the product A times B is symmetric, then the transpose, A times B is the same as its transpose, which is the product of the transposes in reverse order, where B transpose is the same as B, and A transpose is the same as A, and hence the product A times B commutes. Conversely, let A and B be symmetric, and suppose that the product of A and B commutes, then the transpose of A times B is the product of the transposes in reverse order, where once again the transpose of B is the same as B, and the transpose of A is the same as A. And as the product commutes, this is the same as A times B, and hence the product A times B is symmetric. So as an exercise, let A be an M by N matrix with real entries. Show that the products A times A transpose and A transpose times A are symmetric. As a second exercise, find the matrix A where the inverse of 5 times the transpose of A is the 2 by 2 matrix with rows -3, -1, 5, 2. So new definition: a square matrix A is skew-symmetric if and only if A is equal to the negative of its transpose. So as a third exercise, let A be a square matrix of order n with real entries. Show that A can be expressed as a sum of a symmetric matrix and a skew-symmetric matrix of the form A is equal to 1/2 the sum of A and its transpose plus 1/2 the difference of A and its transpose. That is, show that this sum is equal to A and that one of the two matrices, A plus A transpose or A minus A transpose, is symmetric, while the other is skew-symmetric. So new definition: let A be a square matrix of order n with real entries, an elementary product of the entries of the matrix A is any product of n entries where no two entries are in the same row or the same column. So let's look at an example. We'll start with the simplest case, 2 by 2 matrix A with entries A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2. So there are two elementary products. If we choose the entry A sub 1, 1, then the only entry in the matrix that is not in the same row or in the same column is the entry A sub 2, 2. And if we choose the entry A sub 1, 2, then the only entry in the matrix that is not in the same row or the same column is A sub 2, 1. And so these are the elementary products of the entries of the matrix A. So notice that A sub 1, 1 times A sub 1, 2 is not an elementary product. Since A sub 1, 2 is in the same row as A sub 1, 1. Similarly, A sub 1, 1 times A sub 2, 1 is not an elementary product. Since A sub 2, 1 is in the same column as A sub 1, 1. And notice, once again, that there are 2 factorial, or 2 elementary products. So next, we'll consider a 3 by 3 matrix B So the elementary products are as follows. If we choose as the first factor B sub 1, 1, then we have 4 choices for the second factor that are not in the same row or the same column. If we choose B sub 2, 2 as the second factor, then we only have 1 choice for the third factor, and that is B sub 3, 3. Now, if instead we choose B sub 2, 3 as the second factor, then we only have 1 choice for the third factor, and that is B sub 3, 2. Now, if we choose B sub 1, 2 as the first factor, then we have 4 choices for the second factor that is not in the same row or the same column. If we choose B sub 2, 1 as the second factor, then we only have 1 choice for the third factor, and that is B sub 3, 3. Now, if instead we choose B sub 2, 3 as the second factor, then we only have 1 choice for the third factor, and that is B sub 3, 1. And if we choose B sub 1, 3 as the first factor, then we have 4 choices for the second factor. If we choose B sub 2, 1 as the second factor, then we only have 1 choice for the third, and that is B sub 3, 2. And if instead of B sub 2, 1 we choose B sub to 2 as the second factor, then we only have one choice for the third factor, and that is b sub 3, 1. So notice that there are 3 factorial, or 6, elementary products of the form b sub 1 j sub 1 times b sub 2 j sub 2 times b sub 3 j sub 3, where j sub I is an element in the range from 1 to 3, and j sub I is not equal to j sub k for any I or k in the range from 1 to 3.